Okay, so we have a set of 9 exciting and short talks. I'm very excited to be kicking things off. The talks will be about 6 minutes, and there will be exactly 1 question each. But fear not, if you have a penetrating question that you need to ask, or maybe a series of questions to really grill the authors, all of the WIP authors have a poster in the session immediately after this one, and will be available for 2 hours to field questions. All right, so our first speaker is Jie Zhang from Cloudera, and he's going to teach us about how to build erasure coding support in HDFS. And one of the jobs of session chair is to shamelessly plug people who are seeking jobs or seeking employees, and Cloudera is apparently hiring. With that, I'll hand it over to Jie.
Thank you, Don, for the introduction. Good afternoon. Today I'm here to present a joint effort in the Hadoop community to build native erasure coding support in HDFS. The project was initiated by Cloudera and Intel, and HoughtonWorks and Huawei have also joined the effort. So with the fast-growing data volumes, recently many distributed storage systems have adopted erasure coding. As we can see, there's a clear trend, and is HDFS yet another distributed storage system using erasure coding? We have identified a set of unique research challenges. So first, HDFS has to support heterogeneous requirements on data layout. Traditionally, MapReduce like Workload, they have a high requirement on working on local data. But a recent trend is to support parallel I/O from multiple spindles. Also, HDFS is a Java-based single master system, so we need to be sensitive to the master node workload. We also need to support a rich set of existing HDFS features such as flush, append, truncate. And we'd like to make the codec framework really generic. We want to support configurable and pluggable erasure codes, and we even want to support dynamic algorithm selection based on the workload. And we want to support efficient transformation between replication and erasure coding forms. So first, I want to highlight the research challenge around data block layout. So in a distributed storage system, a block can be stored in 2 different fashions. First, we have the layout called Contiguous Layout, where each server can host a large contiguous chunk of data. So this is good for locality-sensitive applications because they will have the opportunity to work with a large sequential chunk of data. But in the context of erasure coding, it doesn't efficiently handle small files, which are smaller than a full group of blocks. So then there's the layout which stripes data in small units across multiple servers. So it improves I/O performance under high-speeding network because the disk drives on multiple servers can work in parallel, but it will break even a small file into even smaller blocks, and it will impose heavier memory and CPU overhead on name node or master node. As we survey the literature, we have seen each layout to support both replication and erasure coding. As we can see in the lower left corner, the current HDFS uses replication on the contiguous data layout. And the eventual goal of our project is to support all 4 combinations and the efficient transformation across them. Then the second challenge I want to highlight is the master node workload. Under the striping layout, many small blocks are created. To address this, we plan to use predictably named blocks where each block ID has a block group ID and the index in the group. These will allow an entire block group to be tracked as a single block with multiple locations. So we further propose to use fixed placement groups or even peer monitoring among the data nodes. And now I'd like to show some preliminary results from our cluster profiling. We get the metadata from 3 large production Hadoop clusters. As we can see in cluster A, Although almost all files are small, those 2% large files, they account for over 60% of storage space. And cluster B has a much lower Gini coefficient, and the top 2 large files contribute to only 40% of the storage space. And cluster C, in cluster C, we see small files dominate in both file count and space consumption. As a result, if we apply contiguous layout erasure coding to the 3 different clusters, we can see in cluster A, it still have a significant saving because the large files, they account for a large portion of the storage space consumption, but in cluster C, it has almost no savings. Regarding memory overhead, we can see the striping layout without our optimization, it has over up to 500% memory overhead, but with our optimization, it's much lower. Then we plan to support generic codec framework through a generic interface plugged with different erasure coding zones. For example, you can have an archive zone with more storage saving but higher reconstruction cost, and vice versa. These are some implementation details I will skip, and I want to highlight we'd like to incorporate fast hardware-assisted coding algorithms contributed from Intel storage library. I think I have 1 minute left. So the quick takeaways, we want to build native erasure coding support in HDFS, and we'd like it to be a vehicle for continued innovation around erasure coding. So if you're interested in contributing, just search for the magic number HDFS 7285.
All right, well, if there are no questions, we'll invite Joel Frank to come up, and he's going to tell us how we can search a secret split data store, which I don't like to keep all my secrets in one place. So.
Good afternoon. Hopefully nobody's fallen asleep quite yet. My name is Joel Frank, and I am going to talk about how to search a secret split data store. Sorry about that. So the system we're working on, anytime information privacy is of vital concern over a long-term data store, secret splitting on a distributed architecture is the perfect choice. It gives you independent sites. None of your data exists all in one spot. Minimizes the threat of insider attacks. It allows you to operate while compromised, because of course in any long-term architecture, it's not a question of when you get, or if you get compromised, it's a question of when. So in order to maintain that privacy over the long haul while you actually have a whole site being compromised is critical. The problem is, now that you've done all this work and you made your information nice and secure for the long haul, you made it so secure you can't search it. So that's where our project comes in. Because historically, in order to search it, you either had to reconstruct your data, which of course reintroduces the single point of compromise and or failure, which you just did all this work to avoid. And it's also just computationally infeasible to do during any kind of operating system. So what you end up doing is you have to pre-index your data somehow, right? You have to attach some kind of metadata, some kind of tag, some kind of identifying information to these secret split pieces so that you can search them. The problem is, historically, all these methods have been based on fixed key encryption. And of course, in a long-term data store, that's not the optimal choice for many reasons. So our goal of our project is to achieve that without fixed key encryption. So if we take a look at what a secret split data store really is, you take your data, you split it into pieces, you distribute these pieces into your architecture, and then you maintain some kind of pointer, some kind of identifying string or whatever to find your pieces again, right? So ultimately, in order to search this, what we really need to do is we need to make the connection between a search term and a document ID, a list of document IDs that actually has that search term, okay? And this is exactly what our system does. We pre-generate and store all these queries and associations between search terms and secret split document IDs and then secret split those queries and store those in a query layer on top of our data layer. And I want to point out that in our system that the query layer is actually agnostic of the data layer, so it can be built on top of pot shards, clever safe, any mechanism you want. The underlying data secret splitting mechanism is not, our algorithm is not dependent on whatever you choose to secret split your data. So where is our system right now? Right now we are testing on digital corpora, which is approximately 1 million files of varying types. We do some pre-ingestion, but again, that's not critical to, sorry, let's bring it up there. Our process of ingestion has nothing to do with how you may ingest. This is what we're doing for our test bed. We're stemming our files, identifying keywords in that manner. We've implemented our system using JEratio on the front end and a Berkeley DB on the back end as our key value stores for our clients and our data servers. And our next steps are really to evaluate and hammer our system and get some real performance analysis, as well as look into reconstruction aids so that recombining your secret split data is not such a giant combinatorial problem as it can be. Obviously, I just glossed over a whole lot of details. I don't have a lot of time, so that's why. But if you have feedback, concerns, questions, suggestions, I would love to hear from you, so please find me during the poster session. That said, if you have any questions, please let me know. Thank you.
All right, quiet crowd. Want to use your laptop? Or you
Yeah, you can use mine. Huh? Are you using my laptop? Yeah, I use yours.
Okay, well then you need to. Oh, I see. You need a. I think you may have to stand up. Do we have a portable mic that she can use sitting down? I'm sorry. All right, while we're getting set up, our next speaker is going to tell us about how to build entangled storage. And this is Veronica Galananez. And you know, this makes me think of my favorite quote from the Peanuts cartoon, where they're asking, why do mountain climbers tie themselves together? And the answer is so that if one of them falls, they all fall off the mountain. But hopefully that's not why we're building entangled storage.
Okay, hello. Can you hear me? Yes. So good afternoon. I'm Veronica Estrada. I'm in third year of University of Neuchâtel. My PhD advisor is Pascal Felber. So the motivation of this research is long-term retention data. So for that, we want to tolerate large amount of failures. We want to use simple and cheap encoding methods. And we want to propagate redundant data across all redundant storage devices in a data center. So this is what we have currently in cloud storage. Simple is beautiful. If we want to protect a CATS file, we just need to copy the file 3 times. But this is not storage efficient. So then there is another way of doing that, that is Reed-Solomon. In this case, we split the CAT, well, not the CAT, but we split the file CAT in pieces, and we disperse the information and get encoded blocks, also that we can use as wildcards. So basically, both methods can tolerate the same amount of failures, but the second one, Reed-Solomon, use less space overhead. But there is a problem. There are shortcomings with Reed-Solomon. One of them is repairing single failures. So in data center, there are more than 90% of the failures correspond to single failures. There's also another problem that belongs to both methods. If we want to increase redundancy in the system, we require more storage. So we want to increase the redundancy of the system without increasing the storage, and our answer is helical entanglement codes. So the idea of helical entanglement codes is to mix all data, all parities that are stored in the system with new data. So, and we propagate with data across the whole system. The idea of propagation, we took the idea of a DNA-inspired topology in which we create strands or chains of entangled data. These chains of entangled data are user and parity data that are generated by XORing all data that is in the system. And each block is XOR with 3 old parities, creating a horizontal and a double helix strand. So in fact, here we can see the left-handed strand. And in fact, we have P double helix strands. So why this topology is important? So the thing is that these P helical strands define a window, and in this window we have 8 P blocks that are strongly interconnected, interdependent. Then if we can tolerate a large amount of failures inside this window by using these strands to use the remaining data that is in the system to recover from failures. But PHEC is non-MDS code. That means there are some minimal erasure patterns. So if we want to talk strictly about the fault tolerance that we can tolerate, we have to see that this is the minimal erasure pattern that HEC can tolerate. So HEC can tolerate P plus 5 failures. So it's strictly related with the number of strands that we use. So let's see how we can build this in an entangled storage. We are studying block placement, since block placement affects the fault tolerance of the system. So as an example, we see how this placement works when we use Reed Solomons in Facebook. Facebook in the F4 system use an independent cell that comprises 14 racks, and each rack contains 15 hosts with homogeneous devices. And when using a Reed Solomon stripe of 10 data blocks and 4 parities, we can distribute this block in each rack. So then we have 14 failure domains, distinct failure domains. But in the case of HEC, if we use a simple example, it's a 5 HEC with 5 double helix strands, there are 80 blocks that are strongly interconnected, and they should be placed in different domain failures. So the trick to do that is to use a minimal erasure pattern and to use only the blocks that belong to this minimal erasure pattern, and then we require less number of racks. And we can use this infrastructure, like 14 racks, to support all the failures that a 5 HEC can tolerate. So another important thing is that HEC is very flexible, and for instance, single failures that we call here local, when there is only one failure, we can recover the block with an XOR and contacting only 2 nodes. In global incidents, where there are many failures, we can use a repair tree. HEC also tolerates 4 levels of failures. And as a comparison, we can see that if we increase the number of stripes in HEC, we can increase the fault tolerance while maintaining the storage overhead constant. And we also need to contact only 2 nodes in the case of single failures. Finally, it is important to say that in replicas and Reed Solomons, we have 100% of loss when all the devices are missing. But in the case of HEC, we just lost 2 data blocks. More details I will give in the poster session, so please come to visit it. There was a lot of.
All right, Taeyong. Okay, our next speaker is Taeyong Kim, who will be teaching us about I/O virtualization for SSDs.
Hi, good day. My name is Taeyong Kim, the first writer on this research. The title is Improving Performance by Bridging the Semantic Gap Between Multi-Queue SSD and Quick Emulator I/O Virtualization. First, look at this background. As you know, Multi-Queue SSD has a lot of queues for I/O requests to improve parallelism on multi-core system. The best example is non-volatile memory express SSD, and it can achieve its performance up to 750 kilo IOPS. Now we should pay attention to a new interface between hypervisor and storage. NVM SSD uses PCI Express as a hardware interface and NVM Express as a software protocols. It mainly supports 64,000 queues and 2,000 interrupts. These features can improve not only parallelism, but also performance. For these reasons, NVMe SSD consequently causes several unknown problems even in OS. There was already an issue in Linux block layer, so some researchers observed performance degradation on I/O scalability. This is largely because the block layer waits to acquire the lock whenever it sends an I/O request from the single request queue to the SSD. To solve this problem, previous work proposed 2 levels of queue architecture. However, Quick Emulator also has another problem in virtualization. In our evaluation, performance dramatically decreased by 74%, and we suspected that this problem was caused by semantic gap between multi-queue SSD and Quick Emulator. Fortunately, until now, this issue has been concealed because of the low performance of storage. Now we look at this old architecture. Quick Emulator uses Bataille block data plan, which is an outstanding para-virtualized I/O technique. Basically, Quick Emulator operates on a single process which has per virtual core thread, single shared circular queue, and single I/O thread. Like you see, the dedicated virtual core thread have to issue I/O request after holding the lock on this shared queue. As a result, Quick Emulator suffer from the frequent lock contentions, especially in scale-up I/O. Furthermore, single I/O thread cannot deploy multi-queue here because it submits I/O requests to just one queue in host kernel. This picture shows that current architecture partially utilizes multi-queues in OS and SSD. Next, let me introduce our architecture. In our research, we propose a new approach to solve both the lock contention and the scalability issue. It's multi-queue and multi-IO thread architecture. To distribute the lock contentions, we first eliminate a single circular queue and then allocate a dedicated queue for each virtual core. This can minimize the lock contention among virtual core threads. Second, to mitigate a scalability issue, we also improved the parallelism of I/O requests by using multi-I/O threads. This is because each multi-I/O thread can submit I/O requests to separate queue in host kernel. For these reasons, our architecture is able to fully exploit multi-queues in OSN SSD. Finally, this is evaluation. In conclusion, I/O performance was significantly improved by up to 2.5 times, and the performance degradation completely disappeared on varying the number of jobs 1 to 8. There are 3 experimental groups on 4 different workloads by FIO benchmark. The blue one is a reference group, and the green one is a previous work which has a multi-queue feature. Then the red one is our work. On 4 kilobyte random read, our architecture achieved 380 kilo IOPS. But in blue and green groups, we can even find the performance degradation when the number of jobs is increased. To summarize, we obviously resolved the rack contention problem and the I/O scalability issue in quick emulator I/O virtualization using multi-queue SSD. That was done, and thank you for listening. And any questions?
All right, quiet crowd. All right, so our next speaker is Zhi Zheng, who's going to tell us what non-volatile memory can do for GPUs.
Good afternoon, everyone. My name is Jie Zhang from the University of Texas at Dallas. I'm working in Computer Architecture and Memory System Lab with Dr. Miu-Su Zhang. Today, we will present our work, Shared Non-Vital Memory Cache for Energy-Efficient High-Throughput GPU Computing. Our work mainly focuses on the cache thrashing and the congestion problems. That is, when the thread's working set is larger than its resident set, it will cause multiple data exchange between the last level cache and the main memory, which will degrade the cache performance. From architecture point of view, the impact of cache thrashing depends on the active threads and the cache size. Because of this feature, GPU experiences a much worse condition of cache thrashing. So let's take an example. For the CPU i7-4770K, it uses 8 MB last level cache, which is shared by 8 threads from 4 cores. But as for the GPU, GTX 680, it only uses 500 KB last level cache, which is shared by over 1,500 threads. The limited space of last level cache, as well as the massive threads makes the cache thrashing very compelling in GPU research. The prior thread sorting scheme can mitigate cache thrashing by sorting the number of active threads. It can reduce the cache contention in last level cache. But the problem is it is not aligned to the massive parallel execution model of modern GPU architecture. Also, it cannot fully utilize the on-chip GPU resource. Another option is cache bypassing scheme, which bypasses the data block directly to the streaming multiprocessor to protect cache block in last level cache from early eviction. But if the bypassed cache block will be reused later on, it will increase access to the main memory, which results in the challenges of traffic congestions. Different from the prior works, we want to try another way. So what happens if we can enlarge the last level cache by 100 times as the extreme case? If we look at this figure, the performance improved up to 120% as a benefit, but the disadvantage also very significant. So in energy, overhead is quite big, and the area overhead cannot be ignored. So we would like to introduce NVM cache to replace SRAM-based last level cache, which is high performance, low power, and high density. The GPU architecture has multiple single instruction, multiple threads processor. Each SIMT processor employs this private layer 1 cache. The last level cache was attached to the interconnect network, which supports data communication with the computation unit and the shared resource. Our baseline NVM cache replaced SRAM-based last level cache with STRAM of similar area size. We construct a memory line consisting of 8 subarrays, and each subarray has 500 multiplied 500 matrix of cells. Since the feature size of SRAM is 105 f squared and that of STRAM is about 27 f squares, our baseline NVM cache can provide 4 times larger capacity. Since we want to enlarge the capacity further, we introduce 3D Stack Nvm Cache, which pair up 8 different memory layers. Each memory layer has a single predicate logic, and each subarray employs a through silicon vias as its data channel. Totally, 3D Stack Nvm Cache architecture can provide 32 times larger capacity. So from our evaluation, the performance we have the performance benefits up to 60%, and the miss rate is also be reduced by at least 43%. We also can save energy in last level cache and the DRAM. The dynamic DRAM energy has been reduced at least 36.4%, and the last level energy has been reduced 45% on average for the baseline NVM cache, and it is similar behavior to SRAM-based last level cache for the 3D stacked NVM cache. Thank you.
All right, so keeping with tradition, people are completely convinced of everything they've heard, and we will not have any questions. Okay, our next speaker is Hui Wang, and she's going to tell us about how to allocate our bandwidth, and she is on the job market, so please shower her with job offers at the end of the talk. Thanks.
Thank you. Hi, good afternoon, everyone. I'm Hui Wang from Rice University. Today, I'm going to talk about the time-based allocation in hybrid storage system. In hybrid storage system, storage combined HD and SSD. Each device have quite different speeds. Meanwhile, clients also have variable source time and different request ratio on each device. Then there are several challenging problems like how to allocate the bandwidth of multiple resources to each client and what's a fair allocation. And second, how to handle the different device speed and the workload-specific service type. Because what's the throughput and how to improve the system's throughput? What's the relationship to device utilization? Let's start with a simple example for a single device and see how the variable service time is handled. Suppose there are 2 clients with different service times. For example, suppose the service time of client 1 is twice of client 2. for IOPS-based allocation, it will give the equal IOPS to each client, as shown in this figure. So, but for time-based allocation, actually it will give the equal time to each client. So every one request from client 1 will follow by 2 I/O from client 2. So for the total device time allocated to each client, the IOPS-based allocation will actually allocate 2/3 of the time to client 1, and client 2 only gets around one third. It actually throttles the fast client, and it's unfair for the fast client. For time-based allocation, it's a better solution for variable service time. It will allocate the same time for each client, and this is quite straightforward for a single device. When it comes to a hybrid storage system, the problem is much more complicated. There are a lot of additional information for hybrid devices, like for the device have quite different speeds, and also even for each device, client have quite different request ratio, and also quite different service time. Given this situation, what's a fair allocation, and what's the system throughput? A naive generalization of time-based allocation to hybrid storage is using time slicing and treat the system as a black box. For example, suppose there are 2 clients with quite different access ratio. Like for client 1, it has a hit ratio 0.5, which means it has equal I/O request to each device. While client 2, the hit ratio is 0.95, which is 95 of the request goes to SSD. So they have quite different load on different device. If you use strict time slicing, each client is allocated the equal time slice, but they have quite different time usage on each device because of the unbalanced load. So this also system throughput is also low. In hybrid storage system, we guarantee several fair properties for the allocation, like a sharing incentive, which means a client gets at least as many IOPS as from strict time slicing, which is a fair allocation. Another one is bottleneck fairness, which means clients bottlenecked on the same device get equal time on that device. Third is NV freedom, which means clients prefer their own time allocation over that of any other client. The goal is to find allocation that are fair and also maximize the system throughput. So we studied the system, and there's a very important observation that the maximum system throughput is as it happens when both devices are fully utilized, or when bottleneck set is allocated to all the resource, which is quite different with IOPS allocation. In our model, it will take the information of all the clients, like hit ratios, variable service times, or all the clients, as the input, and the output is the allocation to each device, to each client. Generally, there are 3 very important variables, U, V, W, which are very simple function of the inputs. The W actually is related to balancing the load on each device subject to the resource constraints. U and V are defined by fairness constraints. So the maximum throughput is determined by those 3 parameters, and it can also guarantee fairness. We have some preliminary results evaluating the system throughput and also fairness properties. First, we look at the system throughput. Suppose there are 4 clients with quite different hit ratios and variable service times. The left figure actually shows the system throughput for each client. We compared with the strict time slicing and the proportional allocation, and our model could get better system throughput. Second, we evaluate the sharing incentive property. The 2 figures actually show the device time of each client on each device. The first one is the SSD device time, and the second one is the HD device time. For each client, the blue bar is the time get by strict time slicing, compared with the red bar, which is the time allocated by the TBB, our allocation model. The clients actually get at least as many IOPS or as much as device time that from strict time slicing, so the sharing incentive is guaranteed. Third, we also evaluated the NV freedom property. In this figure, the first bar is the throughput of client 2 can get by TBBA model. The next 3 are actually the throughput if if client choose swap the resource with others, it actually gets less I/O. And it's actually true for all the clients, which means no one will envy others' allocation. They will satisfy with their own. So to conclude, TPP model will provide high system throughput and fair allocation, and we also have some experimental validation in progress. There's a lot of details I didn't cover, so if you have any questions, just ask me during the post session. Thank you.
All right.
View menu and enter full screen. The bottom one.
Okay. Let me do this. Okay, so our next speaker, Naohiro Aota, is going to tell us something that should be near and dear to all of our hearts, which is having better coverage for our file system tests.
Hi, I'm Naohiro Aota from Keio University. Today, I introduce about our working project to improve file system test coverage with injected disk snapshot. Let's start with some background. It is difficult to implement file system bug-free. The previous works revealed that new file systems like ButterFS introduce a number of bugs, and also all file systems such as X3 have bug fix patches. Bugs in file system can lead to data loss, so we really need bug-free file systems. And nowadays, test tools are widely used to catch bugs. XFS test is one such tool for Linux file systems. It was originally a test tool for XFS, but now it supports other Linux file systems, including ButterFS and X4. We targeted XFS test to improve Linux file system development. In general, high test coverage is required for a thorough test. So we evaluated coverage of XFS tests on XFS and ButterFS and X4. And we found some interesting impairment listed here. The most important finding is that even simple functionality, like creating a new file, is not covered completely, even for XFS. The people is in XFS directory, and this figure shows the XFS directory, and each directory entry holds an underlying file name, so it has variable length. When creating a new file, it tries to use empty spaces, but if it failed because the new entry is too large, it tries to make a room by compacting the array. However, it actually runs the compaction only when the estimated space available after the compaction is large enough to hold the new entry. For this complexity, XFS tests fail to run the compaction code. So why is the coverage is low? First, it is not easy to cover all execution passes. File system code is large and have lots of branches in code. And second, it is not easy to control execution passes. Execution depends on entire disk images. That means huge space of possible input to file systems. And finally, it is difficult to obtain a desired disk image from a normal operation, a long sequence of system calls is required. So our approach is generate a desired disk image from outside of the file system and run a specific code of Brook. For the compaction case, we can generate fragmented directory, and then we can run the compaction code with one touch. So the problem is how to generate such a desired disk image. And the prime challenge is how to map in-memory data to on-disk data. In theory, we can apply static analysis to reveal all the mapping. However, it is impractical to do so. So we assume we have a test case running near the target code block. With this in mind, we can apply following dynamic data flow analysis to find out the mapping. Our system will first run the original test cases, recording system call parameters, disk snapshots, and execution paths of each system call. And then we analyze the result and find out the nearest system call, and it mounts the nearest snapshot and replaces the nearest system code. Since the image is newly mounted, all the data loading paths are executed here. So we can apply dynamic data flow analysis here to find out the mappings. With this in hand, we can figure out how to modify the disk snapshot. It may require some manual effort. And in conclusion, coverage of XSS tests is not high because the execution process depends on the entire disk image. So we propose generating a disk image to run the uncovered code blocks leveraging existing test cases. That's all. Thank you.
I'm feeling brave. Okay. And then, oh, what do you know? It works.
All right, take it away. So Terrence is our next speaker.
Can everybody hear in the back? Okay, great. I'm Terrence Kelly. I'm here from HP Labs to talk about zero overhead crash recoverability. If you want more details, you can come talk to us at the poster session tonight or look at the HP Labs tech report on the subject that's already posted to the web. We'll be presenting this in some outside venues next month. Okay, so one of the reasons why byte-addressable non-volatile memory on the memory bus is exciting is that it creates new opportunities for dealing with failures. So in this talk, we're going to mainly focus on things like kernel panics and power outages. In order to survive a failure, data must find its way from programs that modify data all the way down through vulnerable things like CPU caches and DRAM to the safety of block storage. And today, that's rather slow and expensive. NVM dramatically reduces the distance between the programs that alter data and the non-volatile memory that where data is preserved across crashes. And that's one of the game changers of byte-addressable NVM on the memory bus. It dramatically reduces the cost of putting data in a place where it will survive common kinds of failures like kernel panics and power outages. So in a world of non-volatile memory, one way to ensure that recovery code can find data following a failure is to flush cache lines. That's how you push data from the processor cache down into NVM. Well, this can be slow. It's a lot faster than calling fsync, but it's still slow. It slows you down. An alternative approach that is sometimes implementable is to not bother with cache line flushes during failure-free operation, but instead detect when a failure is imminent and then flush the whole cache to rescue your data just in time at the last minute. This latter approach I will refer to as flush on failure. Okay? Now, even if you have flush on failure support, you're not done yet, because in some sense you have allowed the enemy, the failures, to decide when data is made durable. And that's a problem because applications want to update data transactionally in all or nothing fashion, even if CPU caches are now effectively safe because you're going to rescue their contents at the last minute when a failure is imminent. A failure can still leave the state of application data in NVM inconsistent. In general, therefore, we require recovery code, non-trivial recovery code, to reconstruct a consistent state of data in NVM following failures. HP Labs has introduced a general-purpose NVM programming platform called Atlas, which we described in a paper last October at UPSLA, that uses undo logging to ensure consistent recoverability of application data in NVM. It operates in two modes. It can flush data down from CPU caches into NVM during failure-free operation, or if flush on failure support is available, it can rely on flush on failure support, which is much faster. Now, one problem is that the overhead of logging during failure-free operation and recovery following failures still remains. Let's see if we can get rid of that overhead. There's a class of mechanisms called lock-free and wait-free algorithms that are used for handling multi-threaded isolation. They use atomic hardware instructions like compare and swap to update memory, and they provide two important guarantees. The first is that all threads observe a consistent state of application data. And the second guarantee is that if a failure halts or kills some subset of threads, the remaining surviving threads can make useful forward progress. In order to reason about how lock-free and wait-free algorithms interact with flush on failure, we're going to borrow a concept from a very nice paper that came out of the University of Michigan about a year ago called the recovery observer. The recovery observer is a hypothetical imaginary thread that is created at the instant when a failure wipes out all of the real threads in a program. The recovery observer contemplates the state of memory at the time of a crash. Well, when you think about it, if you have flush on failure support, that means that real recovery code sees exactly the same state of memory as our imaginary hypothetical recovery observer. And by definition of lock-free and wait-free algorithm, that means that real recovery code, just like the recovery observer, sees a consistent state of data and can make useful forward progress. And you get this for free. The developer expends no additional overhead beyond solving his problem with lock-free and wait-free algorithms. There's no additional failure-free overhead. There's no additional recovery time overhead. So to summarize, flush on failure can eliminate the need to make data durable by things like cache line flushes during failure-free operation. Non-volatile memory dramatically reduces the cost of flush on failure in both time and energy. Lock-free and wait-free algorithms update data atomically without logging, and you connect the dots and you realize that you can achieve zero overhead crash recoverability. And now I'll be happy to take questions.
One quick question. Now, this does assume particular behavior on the part of the memory on power fail. So, in fact, for some of these, you're assuming that a write happens completely or does not happen completely.
Yes, that's right.
Thank you.
All right, let's thank our speaker. Sorry. After you, please. All right, our final speaker is Stephanie Jones, who's going to tell us a little more about shingled disks in case we haven't had enough yet. I know I haven't.
All right, hi folks, my name is Stephanie Jones. I'm here to talk to you about data separation to reduce data movement in shingled write disks, also known as shingled magnetic recording drives. I know that Skylight gave us a little of an overview, but let's recap real quick. So Shingle disk layer tracks like shingles on a roof. The example on the right here, each blue band would be a track. So, 1, 2, 3, 4, 5, you can see the track width for each track here. We're taking advantage of the fact that the read head is smaller than the write head. So, for example, that would be your the read track width. So what we're doing is we're scooting the bands closer together and layering them, again, like shingles on a roof. But the problem is say I want to write back to track number 1. Well, I end up destroying what was in track number 1, which is fine. But then I completely demolish what was in 2 and probably partially overwrite what was in 3. So we can't do random writes or in-place updates anymore. So what's the problem here? The major bottleneck for what's going on here is band compaction. This is how you reclaim space in shingle write disks. This is what the gentleman from Skylight was saying was the read, modify, write. So how do we approach band compaction? Well, our work is focusing on minimizing the long-term data movement when performing band compaction. We're proposing using write heat as a metric to reduce long-term data movement. And what I mean by write heat is the more frequent you see writes to a particular LBA, the warmer and warmer it's going to get. So why do you need to classify data? Well, you can end up moving fewer blocks during band compaction. What I'm talking about here is if you can separate your cold from your hot, cold being data that's written once, read as many times as you want, but is never overwritten, you can isolate these in bands, and then you won't have any holes when you update them, and then you can ignore an entire portion of your disk when you're doing band compaction. This can improve system responsiveness. It will reduce overall system activity. We've done this using a simulated log structured file system with a block-based API, doing 2 and 4 band compaction. Our pseudocode for multiple band compaction is to read all the live data in the multiple bands, sort in ascending order by block write heat, write the live data to one of the bands that we've read from. If the band is full and then and there's still live data, we will write to another of the bands that we've read from. We do band compaction on demand. We're not aggressive. This is how we do it. So heuristics for block classification. We developed and tested 3 heuristics. First one is empty. We're straightforward. It's our naive. We compact the emptiest bands. The second one we call reusability. We're compacting the bands that have a combination of hot and free, and I will explain that when I get to it. Reusability and segment heat is you use the same formula from reusability, and the result that you get from that formula we multiply by the total heat of the segment. The latter 2 heuristics here classify data blocks using write heat. So empty, we're going to write to all of the segments in the log, and I know we're talking about shingle disk, but I'm using log structured terminology because that's how I simulated it. But when you reach the log's tail, you prioritize writing to any segments that are now empty because you've overwritten the data somewhere else. And if there happen to be no empty segments, you will pick the segments with the least live data. 2 if you're doing 2 band compaction, 4 if you're doing 4. Reusability, the formula is up top, percentage free plus the percentage of hot blocks. So you're taking into account how much of your segment is free and then how much of it is hot, because we want to avoid moving cold blocks as much as possible. So in the first one, we've got half of it free and 1/6 of it is hot, so you've got 1 hot block. In the second one, half of it's free and 1/3 of it's hot, 2 hot blocks. You always want to select the segment with the larger value from the formula because that's going to give you the answer of which is the most free with the most hot, which would be the second one, and if we were doing single band compaction, I would be picking that. Reusability plus segment heat, formula again is at the top. As I said, we're taking the same formula from reusability and we're multiplying it by the total heat of the segment. So cold blocks in a segment would have just a heat value of 1, and then you've got in the first example, you got a block with a heat value of 4. Gives you total segment heat of 6, so we're taking that same result, multiplying it by 6, repeating it for the second segment where you've got 2 hot blocks, 1 with 3, 1 with 2. The second one is still hotter, so we pick that one. Excuse me, and that's how we select segments for band compaction. We also implement a write buffer in order to more accurately separate hot and cold data before it is written to disk. We use a 2-segment write buffer. The size varies based on whatever we're testing. We test 40, 80, 160, and 320 megabyte segments, so double that and that would be our write buffer. When the write buffer is full, we determine if it has more hot or cold data. If it has more hot than cold, we write out the hottest of the data to a full segment. If it has more cold data than hot, we write out the coldest data to a full segment. Some of our future work is to compare to LFS's cost-benefit policy. As we believe that a log-structured file system will work well with shingle disk, it makes sense to compare to the LFS's cost-benefit policy. We need to decide on a realistic method of aging the log using the trace's real data. As it turns out, even using an 80 megabyte write buffer with the traces that we use, which are the MSR Cambridge traces from the write offloading paper that appeared in this conference in 2008, we actually absorb all of the writes, and I never get to do band compaction, which is kind of unpublishable. So we also need to extend the trace data to see if repeating the workload has any impact on our heuristics, and we are going to vary the size of the write buffer and measure the impact that it also has on our algorithms. Thank you.
Hi. It seems to me that the notion of using the hot data, which is the things that are being rewritten, is counterintuitive to me, because it seems like something that's being written is likely to die soon and you won't have to move it. So can you explain a little bit of that intuition?
So the intuition here is actually more focused on the cold and the fact that if you have a mix of hot and cold in your segment or in your bands, you're constantly going to be moving those cold segments unnecessarily as you're cleaning. So by focusing on isolating the hot and the cold stuff's written once and never written, assumingly never written again. So you want to isolate that stuff. And the idea here is that if you can get a lot of hot data moving around, sure, it will invalidate, but chances are you're going to have more empty segments. There's going to be less live data in those.
Okay. We can take it offline. I'll talk to you at your poster.
Okay.
Did you consider the scaling issue of trying to keep track of the heat at small enough increments?
One more time?
Did you consider the scaling concerns around keeping
Yes,
track
I
at
did.
small enough increments?
Absolutely. Right now, reusability would be the best one because you can kind of store it as a bitmap since I'm only counting, whether or not the block is hot, how hot it is. But we're looking into figuring out how to do reusability plus segment heat in a smaller form.
That was my question. Okay. All right, let's thank our speakers one more time.